What is up, guys, and welcome back to the Maths Guy. Today we are starting something pretty cool. We are starting our Year 6 Algebra. And in this lesson, we're going to cover 7 units, starting from an introduction to algebra. Then we're going to look at using simple formulae, then linear number sequences. Then we're going to look at how we can use algebra to help us with missing number problems. Then we're going to look at 2 unknown variables. And then we're going to look at using algebra to help us find missing lengths and how to find missing angles. So let's waste no time. Let's get into Unit 1, which is an introduction to algebra. Let's go.
Okay, so the very first thing you need to understand is that algebra is very similar to arithmetic. It uses the same 4 operations: addition, subtraction, multiplication, and division. But algebra introduces a brand new aspect, and that is the aspect of the unknown. When you are first looking at arithmetic, the only area that's unknown is the answer. So if we look at a very basic one, 5 add 10 equals unknown. The answer is not known until we go ahead and complete our question. A very important difference straight away between arithmetic and algebra is when we have an unknown in algebra, we use a symbol, okay? Now, a very common symbol to be used would be X, but you can pretty much use any letter of the alphabet. X, Y, A and B tend to be the 4 main ones used, but you can use any letter. So in arithmetic, we would leave it as this: 5 plus 10 equals unknown. In algebra, we would have 5 add 10 equals X. The X in this case is a placeholder, and it stands for the number that we have not got the answer for yet. So what we have created is a very basic algebraic equation. An equation is just a mathematical term meaning both things are equal. Both things on either side of the equal sign are equal. So it is saying that everything on this side of the equal sign has the same value as everything on this side of the equal sign. So in this example, the equation is telling us that what's on this side, 5 add 10, the known value, has the same value as what's on this side, which is the unknown value that we are going to call X. One of the main aims in algebra is to solve equations, finding out the unknown value, in this case, X. In this example, it's pretty easy to see that we have got 15. 5 add 10 is 15. And all we need to do is add 5 to 10, gives us 15. Therefore, 15 equals X, which is the same as saying X equals 15. Now, this is an extremely easy example of anything to do with algebra. And that is why when you often see algebraic equations, they are a lot harder. And you might be given a much harder example like this. If we had X minus 10 equals 5, that is the exact same equation as if we had 5 add 10 equals X. But it's not quite as easy to tell what X is. So you could look at algebra like a game. You will be given big algebraic equations that it's your job to solve, simplify, and find the value of the unknown values. And we are going to learn a lot more about actually solving equations in future videos. So make sure at this point you like and subscribe to the channel to not miss that. But for now, let's learn some very important rules about how symbols can and cannot be used in equations. So the very first rule you need to know is that different symbols or different letters can be used in different problems to represent different values. So for example, in the problem we just solved, the letter X was used to represent the number 15. But X could stand for a different value in a different problem. For example, if someone asked us to solve 5 add X equals 10, the value of the X in this case is 5. Because in order for the 2 sides of this equation to be equal, 5 would have to add to another 5 to equal 10. So X or any other symbol can stand for different unknown values in different problems. That's fine. But what is not fine is letters cannot stand for different values in the same problem. For example, if we had the expression X add x equals 10, the equation is saying if we add x to x, we get 10. There are a lot of different ways that we can get 10 with 2 digits. We could add 9 to 1, 8 to 2, 7 to 3, and so on. But let's say we represented it as 6 add 4 equals 10. That means the first x, that value is 6. And the second x, that value is 4. This is not okay. This means that different x's would have different values through an equation, and that would become very problematic. So that's not okay. So if you did need to represent two different values in an equation at the same time, you would need to use two different symbols, and that's why we often see x and y. So if you ever see a really long algebraic equation like this one with lots of x values, all those x values have the same value. Okay, so we know that we cannot have the same letter representing two different numbers. But what about the other way around? Can one number be represented by two letters? Yes, we can. And here's a good example. Let's say we have the equation a plus b equals 2. Now, a could have the value of 0 and b could have the value of 2. Or a could have the value of 1 and b could have the value of 1. Or a could have the value of 2 and b could have the value of 0. So in this example, even though a and b are different symbols, they are holding the same value. There will be times where they just happen to represent the same value. And that brings us on to something else that's really important. Did you notice that each symbol could be represented with a different value depending on what the other symbol was representing? For example, if a is 0, then b has to be 2. If a is 1, then b has to be 1. And if a is 2, then b has to be 0 in order for the equation to be balanced and to be equal. So a symbol's value can change depending on what the other symbol's values are doing. And this means that it is variable. These symbols are variables. Their value can change depending on what else is happening around them. So in this example, both a and b are both variables because they can both change, their values can both change depending on what the other one is doing. So it's really common in algebra to refer to all letters and all symbols as variables. Okay, so what have we learned so far? We've learned that algebra is very similar to arithmetic. It uses the same four processes: addition, subtraction, multiplication, and division. But we've also learned that algebra has an unknown value that can be replaced by a symbol. And we often see x and y and a and b being used the most. But there is one more thing that's really important I want to teach you on this video, and it has to do with multiplication. Here are the four basic arithmetic problems: addition, subtraction, multiplication, and division. Although in algebra, you will see division being represented in its fraction form. In arithmetic, all four of these operations will have the same statue. They are the same importance. However, in algebra, we have a king. Our multiplication is the king. It gets some special treatment. And that's because in algebra, multiplication is the go-to, the standard, the default operation. If you don't see a symbol, you are going to multiply. So therefore, if there are no other arithmetic processes shown between two symbols, we are going to multiply. So for example, instead of writing a times b, we can just write ab. And we know that multiplication is implied. Another key word for us. Of course, in this example, we can't actually multiply a and b until we know what values they are. The advantages of this is that it makes a lot of algebraic equations a lot less cluttered and a lot smaller, and you're a lot less likely to make mistakes confusing sometimes x symbol with x the process. So for example, instead of having a times b plus x times y, we can have ab plus xy. Now this rule doesn't just apply when it's two symbols, it is also implied when it's a quantity and a symbol. For example, we don't need to write 2 times x, we can just write 2x. Because there's no other process between them, we are going to imply and we are going to assume it is multiplication. However, we can't use it for just two numbers, two quantities, because if we wanted to show 2 times 5 and we move the times symbol out, it would show 25. And 25 is not the same as saying 2 times 5. So if we're putting two quantities together, we will still see that multiplication sign. But it will still be the case if we are using parentheses or brackets. If we see two pairs of brackets or two parentheses next to each other, without a symbol, we are going to times them. We're going to multiply the values inside each set of parentheses. For example, if we saw this with a plus b in a bracket and x plus y in a bracket, with no other symbol between them, we know that we are multiplying the a plus b times x plus y. So technically what we could do, going back to our 2 times 5, is we could put them in brackets, in parentheses. Therefore, this cannot be confused with the number 25, and we know because there's nothing between them that multiplication is implied. So we would times 2 times 5. Or if we wanted to, because putting two separate individual things in brackets does look a bit strange in maths, we could put one digit in parentheses and leave one out. Again, multiplication is implied because there's no other symbol between it, so we would still do 2 times 5. Okay, so we have learnt that algebra is very similar to arithmetic, but we have unknown values that we need to solve the equation to get to. We've also learnt that in algebra, the multiplication sign is king, and if there's no other sign there, we are going to use that as our default. Now I know what you're thinking, is algebra useful? Why am I learning this? And the answer is yes, they are hugely important, and that's very difficult to see when you're just looking at a bunch of numbers and letters on a page. But when they become very obvious and very helpful is when we start to graph these equations. For example, there is a whole group of algebraic equations that are called linear equations, and that is because they create a straight line across a graph. Those kind of equations are really helpful to tell you the slope of a ramp, or how long it's going to take to get somewhere or do something. Another class called quadratic equations can be used to design telescope lenses, or to describe a trajectory of a ball that's thrown, or predict the growth of population. So algebra is used all the time in fields like science and engineering and other forms of mathematical careers. And if you ever wanted to set up your own business, you would use algebraic equations to work out your profits and work out your potential profits. So this is a really interesting and exciting avenue of maths.
Okay, so now you've had an introduction, let's look at some simple formulae. Let's go. Okay, so today hopefully we're going to learn what is a formula, how to solve a formula, and then how to write a formula. So let's begin by thinking about what is a formula. And I want to just show you this rectangle, because this is going to be our first example of where we could use a formula. So let's imagine we were trying to measure the area of this rectangle. So we know that we would have to find the measurement of the length and the width. So for this rectangle, let's say the length is 10 centimeters and the width is 5 centimeters. And therefore to solve the area, I would have to times 10 times 5, which equals 50 centimeters squared. So what we've just created here is a numerical equation. We have numbers, we have an equal sign, we have an answer. But there's another way of solving this rectangle, and one that would work solving every rectangle. Let's jump into looking at a formula. Imagine now that we replace these measurements with a variable, a letter, and we call the length A and we call the width B. And what we're trying to work out is the area, this shaded blue area, so we're going to call that C. Now, instead of being a numerical equation, we're now going to create an algebraic equation, because we've now got these variables, these letters that take the place of a number. So if I wanted to write my equation now, I would write A times B equals C. And actually there's a bit of a trick, because when we're doing multiplication, we don't actually need to write the multiplication sign, we can simply write A and B. And when two terms are together like that, the A and the B, without any operation sign, we know that we have to multiply. So I can just write AB equals C. And now what we've just created here is a formula. And this formula will work with every rectangle. All we would need are the measurements of A and B to substitute into our formula. So let's have a look and see if this formula can be used for another rectangle. So now I can write down my formula. We think A, B will equal C, this shaded area we'll call C. And now all I'm going to do is substitute in my numbers to get my answer. So A can be substituted with 4, so I could write 4B equals C. And then I could substitute B with 9 and end up with 4 times 9 equals C. And you can see I've had to put my multiplication sign back, otherwise I would have ended up with 49, and that could be misinterpreted and misunderstood as being just the number 49. And now I can solve my algebraic equation by doing 4 times 9, and 4 times 9 is 36. So my answer would be 36 equals C, or C equals 36. So the formula A, B equals C is very useful, but very basic. But this formula will always work when finding the area of a rectangle. Okay, let's see how else formulas can be used. Let's look at this statement. The cost of food for a wedding is £300 plus £9 per person. This rule can be written as a formula, and the formula would be C, and in this case C will stand for cost, equals 300 plus 9 times n. Let's break down our formula here and just make sure we understand every element of it. So the C at the start is the cost, and the cost is equal to 300 because the 300 is a set fee, a fee for just having a wedding. And then we have to pay per person that's going to come to our wedding, which makes sense, doesn't it? If we're going to have a big wedding, we're going to have to pay more for more people that want to come, and if we have a small wedding, we're going to pay less. And the cost per person is £9. So the 9 is the cost per person, but then we have this times n. What do we think the times n means? That's right, the number of people that come. So n equals the amount of people. Okay, so let's try and use this formula in an example. Let's imagine I'm getting married, and let's say I'm going to invite 40 people to my wedding. Let's find out how much this wedding is going to cost me. So I'm going to start by writing my formula, which is C equals 300 plus 9 times n. And now what I can do is I can start to input some data into my formula. And the data that we have is the 40. We have 40 people coming to my wedding. So I'm going to replace the letter n with the value 40. Because remember, n stood for the amount of people that are going to come. And we know that's now 40. So let's write my second line of my formula, which would be C equals 300 plus 9 times 40. And now we need to use a little bit of our BODMAS knowledge. BODMAS is a helpful reminder for what order of operations we have to do things in. And if I just write BODMAS at the top here, we have brackets, order, division, multiplication, addition, and subtraction. And what we can see here is that multiplication is before addition, so I'm going to do my multiplication first in my algebraic equation. So 9 times 40 is 360. So now I can write the next line. C equals 300 plus 360. Now I'm simply left with an addition question, and I can see that C equals 660. So the cost for this wedding would be £660 based on 40 people coming. But the important thing to understand for this lesson is this formula and the fact that it would work with every amount of people that could come to my wedding. Whether I invite just one person or 40 or 5 billion, I can still use this formula to find the total cost. Now we're starting to see how useful formulas can be. Let's have a look at another one. Marie bakes cakes and sells them in bags. She uses this formula to work out how much to charge for one bag's worth of cakes. So you can see that the cost would be equal to the amount of cakes sold, which are 20 pence each, plus 15p for the bag. So we're always going to have to pay 15p for the bag, even if we buy one cake or if we buy 20 cakes. So let's try and see if we can create a formula for that. So my formula is going to have to start with a C equals, and then let's think back to our previous example when we had a quantity, we used the letter n. So I'm going to do that again, almost like for number of cakes. So n times 20. The number of cakes times 20 pence. But then remember, we have to plus this 15 every time because we have to pay for the bag. So this is what my formula would look like. The cost is equal to the number of cakes sold at 20 pence each plus 15 pence for the bag. Let's see an example of that then. Let's imagine that I buy 2 cakes. So let's start by writing our formula. C equals n times 20 plus 15. And the first thing we're going to do, we're going to substitute the n for my quantity, and we've got 2. So C equals 2 times 20 plus 15. Think back to our BODMAS. Remember that multiplication comes before addition, so I'm going to have to do this multiplication question. So my next line would read C equals 40 plus 15, and now I'm left with my addition. C equals 55, and 55 what? 55 pence. So if I wanted to buy 2 cakes, it's going to cost me 55 pence. Let's see a different example with a higher value and see if the formula still works. Let's buy 500 cakes. Bit crazy, but let's see. Let's write my formula again. C equals number of cakes times 20 plus 15. Now I'm going to substitute my n for my 500. C equals 500 times 20 plus 15. Okay, good. Remember BODMAS, we have to do the multiplication first, so I'll be left with C equals 500 times 20. Well, 500 times 10 would be 5,000, so 500 times 20 would be 10,000 plus 15. Left with my addition question, so it's C equals 10,000 and 15 pence. But again, the important thing to understand is that our formula here, the one that we created this time, would work with any amount of cakes bought. Okay, hopefully you've understood what a formula is, how to write one, and how to solve one. Now it's your turn. Press pause on the video, leave this screen up for a moment, and see if you can work out this question. It says, here is the rule that an electrician uses to work out how much to charge a customer. So the cost in pounds is £25 for every hour worked. But then he also charges a £55 just for coming to your house. So the electrician takes 3 hours to replace some electrical cables and some sockets. Use the rule or the formula to work out how much he's charged his customer. Press pause, good luck. Okay, cool, so that's a pretty big chunk of algebra looked at already. Let's look at algebra from a slightly different side, and let's have a look at now linear number sequences and how we can use what's called the nth term to help us identify any number in that sequence. Let's go. Okay, but first, what is a linear sequence? Well, a linear sequence is any sequence of numbers where the gap or the jump between each of the numbers is consistent. So if we look at this first example very quickly, we can see that the gap between 2 and 5 is 3, the gap between 5 and 8 is 3, 8 and 11 is 3, etc, etc. And therefore, if a linear sequence was plotted onto a graph like this, and these were our terms, so this was the first number, the second, third, fourth, our sequence of numbers would end up being a straight line, a linear line. Now the gap between the numbers can change. It can be 3, it can be 10, it can be 1,000,000, it can be minus 1,000,000. But all linear sequences will have the same gap between each of the numbers. And what does finding the nth term of a linear sequence mean? Well, we can use the sequence to work out the next few numbers. So for example, I know that if the gap between the numbers is 3, this next number on this green row will be 17, because I can just add 3 to 14, which will be 17. I could add another 3, which would be 20. But what if I wanted to find out what the 50th term of this sequence was? Well, I need a formula, and that's what we're going to look at today. So my first thing we're going to do is we're going to find the jump value, the value of the difference between the numbers in our sequence. Then we're going to multiply it by the term, and we're going to understand what that means. And then we're going to find the correction. So that probably doesn't mean too much to you at the moment, but that's all right. That's what we're going to look at here today. Okay, let's have a look at what I mean with question 1, and let's look at step 1, finding the jump value. Okay, so as we said before, the gap between 2 and 5 is 3, 5 and 8 is 3, 8 and 11 is 3, etc, etc. So my jump value for this sequence is 3. And then it says to multiply with the term. So this will be my first term, my second, third, fourth, fifth, and then the one we're trying to find is sixth. And we call these numbers up here the terms. And it just means the number in the sequence. Now, if we think about it, if we're going up in threes, then it's a bit like the 3 times table. So if I multiply my 3 by my term, these numbers here in the blue line, then I'm going to get somewhere close to the sequence value. So to show that, I can write 3 and I'm going to have n for my algebraic letter, choosing n like number. Okay, but like I say, that's going to be close to our number, but not bang on. So then we need to find the correction. Let's see what I mean there. So we know that the next number after 14 will be 17. But so far, all I've got in my formula is 3n, so 3 times the number value, which is 6. If I do 3 times 6, I get 18. 18 is very close to 17, but not quite right. So I need to correct my formula. How can I get from 18 down to 17? Well, I can minus 1. So therefore, my formula for this sequence is 3n minus 1. 3 times the position of the number I'm looking for, minus 1 to correct. Let's check that with one of the other numbers we know. Let's pick this column here, the 4. Okay, and let's use our formula to see if it works. So the first things first, write the formula, 3n minus 1. Now I can replace my n with the number 4 because that's the number that we're wanting. So then it'll be 3 times 4 minus 1. Use my BODMAS knowledge to understand I have to do the multiplication first. 3 times 4 is 12 minus 1, and 12 minus 1 is 11, and that is the number in the sequence. So it works. So I could use this formula to work out any number in this sequence. Let's look at a harder one. So the first thing I need to do again is find the jump value. So I can see this time the gap is 10. Next, what I can do is finish off my table by putting the numbers of the terms on the top. And then to start my formula, I will write 10n, remembering that this n just means the position of the term, the number of the term that we're looking for. So then we can do step 3, which is to find the correction. And to find the correction, we're going to use an example, one that we've got. Let's use this 3. So 10 times 3 equals 30. Well, 30 is close to the 22 that I'm looking for, but not right. So how can I correct from 30 down to 22? I would need to minus 8. So therefore my formula should be 10n minus 8. Let's check it with another one that we've got. Let's check it against the 5th term. So let's start by writing our formula, 10n minus 8. And this time we're going to be looking for the 5th term. So it's 10 times 5 minus 8. BODMAS tells me to do the multiplication first. 10 times 5 is 50, minus 8 is 42, which is the correct number. And again, I can use this formula for any number now in this sequence. Okay, let's have a look at a really challenging one. So first thing we're going to do is find our jump value again. So what's the difference between 11 and 5? Well, it's 5, but it's not just 5, it's negative 5, because we're now descending our numbers. What's the difference between 6 and 1? Also negative 5. 1 and minus 4, negative 5. Minus 4, minus 9, also negative 5. So the start of my formula this time is going to be negative 5n. Okay, then we're going to multiply with the term and find the correction. So let's look at an example with one we've got. But first let's put our term values on the top, our numbers, 1, 2, 3, 4, 5. And we could just pick any example. Let's pick number 4, the 4th term. Negative 5 times 4. Well, negative 5 times 4 becomes negative 20. Okay, so we're close to our negative 4 target, but not quite. So how can we get from negative 20 to negative 4? Well, we would need to plus 16. So it's a little bit confusing because we're in negative numbers, so we have to understand which way round on our number line we're going to start going. If we're at negative 20 and we want to get to negative 4, we actually have to come back up the number line positively, so we plus 16. So my formula would be negative 5n plus 16. Let's see if this formula works with one more in our examples. Let's have a look at the 2nd term. So starting again with my formula, negative 5n plus 16. So negative 5, replace the n with my term, which is 2. Negative 5 times 2, Well, negative 5 times 2 is negative 10 plus 16. Again, BODMAS says do multiplication first. And negative 5 times 2 is negative 10. Negative 10 plus 16 equals 6. The right answer. So it does work with negative numbers too, and it does work if we're descending our numbers. But we have to be a bit sharper to notice that the start of our formula therefore would be a negative, and we need to be aware of what happens when we multiply a negative and add to a negative. And there you go, that is everything you need to know about finding the nth term to a linear sequence. Let's look at things to remember. First, find the difference between your numbers in your sequence, whether that's positive numbers or negative numbers if we're coming backwards. Multiply your difference by your nth term and then see how close you are and find the correction by adding or minusing a number to it. And then finally write your formula. And just check your formula works before you move on, just to make sure you've not made any mistakes. Alright, hopefully that wasn't too difficult. And we're starting to understand a little bit about what algebra is and how we can replace numbers with letters. So let's take that knowledge into our next lesson, which is missing number problems. Let's go. Okay, we've got these 4 questions that we're going to work on. They slowly get a little bit harder, and we're going to try and follow these steps. First, we're going to isolate the variable and first understand what a variable is. Then we're going to do the inverse operation before finally simplifying the equation or solving the equation. Okay, so looking at this first question, we have 2 plus x equals 20. Now, something very important to understand with equations is that we must keep both sides of the equal sign balanced. That is a very important rule of equations, and we must do that at all times all the way through solving this question. So what we're trying to do with step 1 is isolate the variable. We want this x to be on its own. So what we have to do is look at what is attached to it, and we have this 2. We have a positive 2 that's connected to my x. So in order to get the x on its own, I need to get rid of this 2, and the only way to get rid of a positive 2 is to add a negative 2. So I'm going to rewrite my question like this. Negative 2 or minus 2 plus 2 plus x equals 20. But remember what we just said, whatever we do to one side, we must do to the other. So we added a negative 2 to this side. I now must add a negative 2 to this side. So I'll put it here. There we go. Now I can write the next line, and it will say negative 2 plus 2. So this part here is actually just going to cancel itself out and become a 0. So we don't need it, and I'm just going to put my x. So x equals 20 minus 2. Now I can solve this and say x equals, well, 20 minus 2 is 18. So x equals 18. Let's plug it back into the equation and see if it works in place of this x. So ready? 2 plus 18 equals 20. And that is correct, so that works. Let's look at a slightly harder one with a subtraction. Now I have y minus 4 equals 15. So again, all I'm going to do is isolate the variable first of all. So I'm going to have y minus 4 plus 4, we'll get that down to a 0, equals 15. But remember, I've just added this plus 4, so I must add a plus 4 on the other side as well. So 15 plus 4. That way I'm keeping my equation balanced. That's all we've got to think about, making sure that our equation is always balanced. Now I can move to step 3, look at simplifying my equation or solving it, and I can have y. I don't need any of my 4's anymore because my negative 4 cancels out my plus 4. So y equals 15 plus 4. I'll solve this part here now and write y equals 19. Let's check it by reinserting our value into our original equation as y. So I'm going to start with 19, subtract 4 equals 15. Give myself another tick. Okay, let's get a little harder then now. Let's have a look at what this equation means. So now I have 16 equals 4n. And now this part here is a little funny to look at because there's no obvious operation sign. Well, something that we need to understand in algebra, when we have a letter and a number next to each other like this, it is telling us to multiply. So when you see expressions like this without an obvious operation, we have to multiply. So I could rewrite this as 16 equals 4 times n. So I'm trying to isolate the variable by doing the inverse operation or cancelling out what's connected to my variable.
And now the connection to my variable is this 4 times. Okay, so what's the opposite to times? That's right, division. So I'm going to use division now, and I'm going to write 16 divided by 4 equals 4n over 4. So I added a divide 4 on both sides. What does that do to my equation? Well, I can put my first part, 16 over 4 equals, so now my 4 times n will be cancelled out by my dividing by 4, so I'm equaling n. So 16 over 4 equals n. 16 divided by 4 is 4, so 4 equals n, or n equals 4. Let's substitute it back in and see if we get the right answer then. So 16 equals 4 times 4. 4 times 4 is 16. Give ourselves a tick. Let's look at our hardest one then. We have r divided by 2 equals 4. So again, I'm trying to isolate the variable, get it on its own. At the moment, my variable is connected to this divide by 2. So if I want to get rid of a division on one side, I'm going to have to, that's right, multiply on that side as well. So let's do it. R divided by 2 times 2 equals 4. But I can't just leave my 4 like that, can I? Because I've added a times 2 on this side, so I must add my times 2 on this side. Now let's do my next line of the equation, r, and now my divide 2 is cancelled out by my times 2, so I can just keep it as r. R equals 4 times 2, and 4 times 2 is 8. R equals 8. Let's check it by substituting the value of 8 in for r in my equation, and 8 divided by 2 equals 4. Yes, it is. Give myself a big tick. So there you go. That is everything you need to know about one-step equations or missing number equations. Let's look at some things to remember. First, we're going to isolate the variable. We want that variable on its own. And the way we're going to do that is by getting rid of whatever it's attached to by adding the inverse. But remember, whatever we do on one side has to be done on the other side of my equation to make sure that it's balanced. Then finally, we're just going to solve the equation to find the value. Okay, here are 4 questions for you to have a go at. Have a go at answering them, and then put your answers in the comment section. I'm going to mark them all. Good luck.
Okay, now let's have a look at something a little bit more complicated. Let's have a look at what 2 missing variables would look like. Okay, but before we start, let's just remind ourselves what an equation is and what the rules are. So an equation is a statement where 2 expressions have the same value. What do I mean by that? That sounds a bit horrible. Well, this is an expression, and on the other side of my equal sign, this is an expression. And for it to be an equation, these have to be the same value. And sometimes in an equation we can just have numbers, like 2 plus 4 equals 6. This is an equation, but this is a numerical equation. What we're looking at today is an algebraic equation, where we have these algebraic letters, or variables, but it still must be an equal equation. So how do we go about finding the value of these variables in an algebraic equation? Well, we're going to do it by following these steps today. First, we're going to create a table. Then we're going to start with a value for our first variable, and then we're going to use that to find the second variable. Let's see what I mean with question 1. So question 1 says a and b equals 14, and we can sort of think about it like this diagram down here. If we have the total length of 14, then what we're saying is a measures a part of 14 and b measures the other part. But together they will equal 14. So how can we start to put some values on these variables? Well, we're going to do it by making a table. So let's start with a table with a and with b. If we say that a has a value of 1, what we're saying is that this orange a is only the value of 1. So therefore, to find out what b is, b will be the difference between 14 and 1. So therefore we can show that by using inverse. So if I put 14 subtract a equals b, and then replace a with the value 1, 14 subtract 1 equals 13. So in my table, if a was 1, b would have to be 13. Now some of you could probably see that straight away just by looking at 1 and the 14 and realizing the difference must be 13. But it's really important to know how to do it in other ways, because sometimes we're going to get numbers that we can't just do in our head. Okay, let's carry on our table, and let's say that we have a as 2. So again, we're going to use the inverse. So 14 subtract a will equal b. And now we can substitute a with our 2. So 14 subtract 2 equals 12. So therefore b would be 12. And I can do this the other way around as well by starting with b. So let's say I think b is 11, and now I want to find out what a is. I can again use the inverse, but this time I'm going to say 14 subtract b will equal a. And we know the value of b because we've made it up as 11. So 14 subtract 11 equals a. 14 subtract 11 equals 3. So a in this case would be 3. And essentially I could just keep doing this all day. I could find different measurements for a and use it to help me find measurements for b using our equation. But is there a limit? Is there a limit to how many options we would have when trying to find 2 unknown variables? Well, I might get to 5, and then that'd be 9, and then 6 would be 8, and 7 would be 7. And if I wanted to do any more, it would just be 8 and 6, which I've already used. So is this the end of our options for these 2 variables in this equation? Well, no. Because what if I said that a is a decimal number, and the measurement of a is 2.1? Well, let's use our equation again to work out b. So b equals 14 subtract 2.1. So therefore b equals 11.9. So this is another set of potential numbers that could be replaced into our variables. And if we think about it with decimals, I could put a as being 2.1, but I could also put it as 2.11 or 2.112 or 2.1123, and I could go on forever. So we say, as mathematicians, that there are infinite, unlimited amounts of possibilities for an equation with 2 unknown variables, unless we're given some rules to play with. Because imagine if we were looking at this equation here, but they told us that we have to use whole numbers. Well, in that case, these would be our only solutions. Okay, let's mix things up. Let's have a look at this one here. Now, this is exactly the same principle. This is an equation where this side of our equation must be equal to this side. We're again going to start to use a table. But first of all, let's just think about what this means. If we have 2 variables next to each other, without any operation sign between them, what it's actually saying is that we're using multiplication. So this would actually be a times b. It's like a little algebra trick. We don't need to show multiplication, we can just put our variables next to each other. So this equation basically says a times b equals 6. So again, let's build our table. Let's have a and b, and let's look at step 2. We're going to start by creating a value for a or b, but we'll do a. So in this case, let's start with a being 1. And again, we can use our inverse to help us here. So a times b equals 6. So therefore, b must equal 6 divided by a, because division is the opposite of multiplication. 6 divided by a would be 6 divided by 1, and therefore b equals 6. And that looks right, doesn't it? Because 1 times 6 does equal 6. Okay, let's look at another one. Let's use 2 for our variable of a this time. And again, we're going to use our inverse to help us. So if a times b equals 6, b on its own must be b equals 6 divided by a, and b equals 6 divided by 2. So therefore b equals 3. Let's just check that. 2 times 3, and 2 times 3 does equal 6. And again, we could get into some decimal numbers here and start multiplying decimals. We're not going to in this video, but essentially understand that there are still infinite possibilities for these variables. Okay, our last one. This looks a lot trickier, doesn't it? Now it says 2x plus y equals 18. And what it's saying this time is that we have 2x that are going to have the same value. So no matter what we do here, we've got to remember that the x's share the same value. And then we have plus a y. Okay, so how are we going to find out the value of this x or y, or potential values of these x or y's? Well, again, let's start with a table. Step 1. I'm going to have my x over here and my y over here. Now, just incidentally, the x and the y, they could well be a and b, m and n, any letter combination, doesn't matter. So here we go. Let's start again with a logical start, and let's have x as being 1. And what we're doing to our diagram down here is we're saying this is 1 and this is 1, but this y is still unknown. So again, now let's start to think about the inverse, and let's put y on its own. So y would therefore equal 18 minus 2x. Well, we know the value of x because we gave it the value, we've given it the value 1. So we can do the next line, y equals 18 minus 2 times 1. And now I must use my BODMAS knowledge to help me with the order I need to solve this in. And my BODMAS declares that I have to start with my multiplication. So therefore y equals 18 minus 2. And therefore y equals 16. So if x is 1, y would need to be 16. Let's check that by replacing this question mark with our 16 and add them all together and make sure we get 18. 1 and 1 is 2 plus 16 is 18. Correct. Okay, let's do another one, and let's go out of sequence a little bit. Let's say that we're going to say that x has a value of 3. What is y? So we're saying that this x is 3, this x is 3, but we don't know y. We want to get y on its own, so we're going to put y at the start. And y equals the inverse of the operation at the moment, which is addition, so it's going to be subtraction now. So y equals 18 subtract 2x. Well, in this case, x has a value of 3, so it's y equals 18 minus 2 times 3. BODMAS tells me to do my multiplication first, so y equals 18 minus 2 times 3 is 6, so minus 6. Y equals 12. Let's check it by replacing the question mark with a 12 and then adding them together. 3 plus 3 is 6, plus 12 equals 18. Got it right again. And again, for this example, there would be infinite possibilities that could be used as variables. So there you go. That is how to find the value of variables when we have two unknown variables in an equation. Let's look at things to remember. First, we're going to create a table to help identify our options. Then we're going to start by creating a value for one of our terms. And we must remember that there are infinite number of opportunities and options that we can use, unless we are given a rule, like it must be a whole number, or it must be a number greater than 10, etc, etc. Okay, your turn. Here are 3 questions for you to have a little look at. I would like one example of what our variables could be for each of these equations. Put your answers in the comment section, I'm going to look at them all. Okay, now let's start to use algebra a little bit. Let's try and use algebra now to help us find some missing lengths in some shapes. You might have seen these sort of questions before, but you might not have seen how algebra can help us solve them. So let's do it. Okay, so you can see that we have a compound shape here. This is actually a pretty tricky one. We're going to start with something a little easier. Let's have a look at this to start with. And we're going to follow these steps. First, we're going to find the opposite length of the length we're looking for. Then we'll find the length next door. And then we're going to use a formula to help us solve it. Well, you can see here in this example, we have this missing length, x. And now my first step told me that to find x, I need to look opposite. So I'm just going to look opposite until I can find another length. And I can see this length here of 8 centimeters. But in this case, that's not the full length of what I need. I need this full length at the bottom. So my 8 centimeters gets me up to here, but then I need some more. So I'm going to look opposite again, and I can see up here I have 2 centimeters that I'm going to use as well. So I'm going to use this 2 centimeters and this 8 centimeters. So that's what step 2 meant, looking next door. Because this 8 centimeters was not all that I needed. I needed to look next door to my 8 and see that there's a 2 as well. So I'm going to relabel these 2 measurements as A and B. And now to make this into a formula, I'm going to say that A plus B must equal X. Okay, well now let's substitute in our numbers. We have 2 centimeters for A, so it would be 2 plus B equals X. And I have 8 centimeters for B, so 2 plus 8 equals X. Therefore, 10 equals X, or X equals 10, same thing. Okay, but that was pretty easy, wasn't it? Because we could see our opposite lengths really easily and just sort of add them up in our head. 2 plus 8 must equal our x. Let's look at a more challenging one. Here we have this missing measurement x down here. So again, I'm going to follow my steps. Find the opposite length. So what is opposite this length here? Well, I'm going to look over here and I'm going to see this length of 5. Okay, so I think this 5 centimeters is going to help me, but that's not enough. So I'm going to follow step 2 and I'm going to look next door. Well, next door this time means next to my x. So this is my x line. So next door would be this length here. And this length is 3. So I'm going to use this length here. Okay, so let's think about what we know. This length here is 5 centimeters. This length here is 3. And this length here where my x is going to be the difference between 5 and 3. Because if I subtract this 3 away from my 5, I'm going to get this missing length. Or to think of it another way, if I add my 3 to my x, I'm going to get 5. So let's put this into a formula and see how we can do it. So again, let's give these lengths letters or variable values. So this will be a and this will be b. So I could do it this way. This is a bit of a longer way. I could do x plus b will equal a, because this length plus this length will equal this whole total. But remember, with the formula we need to get x on its own. So how can I get x on its own? Well, I can inverse my b. So it would be x equals a subtract b. And in this case, we know the value of a, so x equals 5 subtract, and we also know the value of b, which is 3. So x is 5 minus 3, therefore x equals 2. So our missing length is 2 centimeters. Okay, but there is a quicker way if we're a bit more confident with inverse. We could go straight into putting x on its own, and I could say that x is equal to a subtract b. This requires a bit more inverse knowledge to understand that x, this small value, will be equal to the larger value subtract the other smaller value. So x equals a minus b, x equals 5 minus 3, x equals 2. One less step to do, a little bit quicker. Okay, ready for a challenging one. Here we go. We can actually see that in this one we've got 2 missing variables, 2 missing lengths. We have this x up here and y down here. Let's start by solving the value of y first. So y is this length just here. So my first step says to find the opposite length. Now with this one, I can either come this way or I can come this way for my opposite, because they're both 6 centimeters. I'm going to choose to look at this length here on the left, and I'm going to call this length A. So what other information is here that I'm going to need? Well, I can look next door for my other length, and I can see that next door I have a length of 3 centimeters, and we'll call this length B. Therefore, x is equal to A subtract B, and now we can put those values in. A is 6 centimeters and B is 3, so x equals 6 minus 3, which is 3. So my y value here is actually 3 centimeters. Okay, now I want to find x. X is up here. First things first, I'm going to look for that opposite length, and my opposite length is this great big length at the bottom, 10 centimeters, that I'm going to label A. Now this is where it's a little bit more challenging, because look, if I look next door for my other useful lengths, I can see that I have one length here that's going to be useful, because this is a part of my 10, but I've also got to have this one here. So I've got 2 other parts that make up my whole of 10, or A as we're now calling it. So let's label these. I'm going to label this 4 centimeters B, and I'm going to label this 4 centimeters C. So now x is equal to the long length of A, subtract the 2 smaller lengths of B and C, so x equals 10, subtract 4, x equals 2. Now this is not a very neat way of writing our formula this time, because we don't really want to put subtract in a row like that. So what we'd actually write this as is x equals A subtract B plus C. Because if you think about it, B plus C would be this 4 centimeters added to this 4 centimeters, and then if we just subtracted that combination away from my 10 centimeters, I'm still going to get the same answer. So let's check it. So x equals a, which is 10, subtract b plus c, which is 4 plus 4. And now BODMAS tells me I've got to work out the brackets first. So x equals 10 minus 4 plus 4 is 8. So therefore x equals 10 minus 8, which is 2. Same answer. Just a bit of a better way of writing it. Okay, there you go. Let's think about the things to remember. First, start by finding the opposite length. The opposite length is going to tell you what the total of that length needs to be. Then I can look next door to see the other length that I'm going to need to help me. Then we're going to turn all these lengths into algebraic letters. We're going to create a formula and then solve to find our missing length. Okay, ready for our last unit? We're going to now look at how algebra can help us find missing angles. Let's go. So the first thing we need to remember is that all angles in a triangle will equal 180 degrees. That doesn't matter what shape our triangle is. We could have it this first shape, second shape, or even this third shape. All of the angles inside these triangles will equal 180 degrees. And it kind of makes sense, doesn't it? Because as we open an angle like this one down here, we're going to be closing other angles. So together they all stay 180 degrees. So how are we going to work out this missing angle? Well, we're going to follow these steps. Step 1 says to add the angles that we already have. And then step 2 says we're going to subtract that from the 180 total that we know it is. So let's have a look at this first one together then. And we can see that we have this angle down here of 75 degrees and the top angle of 30 degrees. And we're looking for this angle that's marked X. So we have 75. We also have 30. But we're missing this angle here that we're going to call X. But we know that all of the total equals 180. So therefore it makes sense that if we start with this 180 and we subtract the 75 and the 30, we're going to be left with our X. Or we could say that X equals 180 subtract 30 plus 75. So now I can start to solve this, and again let's start with our brackets. X equals 180 subtract, well, what's 30 plus 75? That's 105. So therefore X equals 180 subtract 105, which is 75. So for this missing coordinate we should have 75 degrees. Now I can double check that by putting that into my bar model. We think 75. And now I can check whether this all equals 175 when I add it together. 75 plus 30 is 105, plus my 75 is 180. Perfect. Okay, let's look at shape B, this one in the middle. And this time we're given an angle of 50, and we're given an angle of 90, a right angle. So again, if I draw my bar model, I know that I have a 90 and a 50. And I know that my total is 180. So this missing gap will be my X value. So again, let's use some algebra to help us. I'm going to start with X equals 180 subtract the sum of 90 and 50. So therefore X equals 180 minus 90 plus 50, which in this case is 140. Therefore X equals 40. So the value of this angle is 40 degrees. Okay, one left. Let's have a little look at this one. And I'm going to do it without my bar model this time, just straight into the algebra. And I have X equals 180 subtract 100 plus 40. Therefore X equals 180 subtract 140. X equals 40. So the value of X is 40 degrees. Simple stuff. Let's have a look at what to remember. Remember first that all angles inside a triangle equal 180 degrees. That is going to be our really helpful fact. First then we add up our two angles that we already have and then subtract that number away from our 180 to get our missing angle. Okay, 3 questions for you to have a little look at. Press pause on the video, take your time and try and see if you can get the missing value of these angles. Press pause now, good luck.
And there you go. That is our first look at algebra.
Algebra can get way more complicated, but if you've got a good understanding of these, that's going to give you a fantastic baseline to work from. Hopefully this video has been helpful for you. If it has, think about subscribing to the channel. We make daily videos here to help you with everything maths, but for now, peace out.